In this video, we're going to continue to look at nucleophilic acyl substitution reactions, this time looking at esters and amides. In terms of reactivity, esters are not that reactive, so they can be converted to amides, they cannot be converted to anhydrides or acid chlorides. So if an ester reacts with an amine, then that will give us an amide, or if an ester reacts with water, then it can be hydrolyzed to give a carboxylic acid. Let's look at the mechanism for ester hydrolysis. So ester reacting with water to give a carboxylic acid and an alcohol. This reaction goes almost nowhere under neutral conditions, so it's either carried out under acidic conditions or under basic conditions. Under acidic conditions, it's actually acid catalyzed. So let's take a look at this mechanism. When we have water and acid, we're going to have H3O+. So the carbonyl oxygen can grab off a proton, put these electrons back in here, and we get our protonated ester. Now water can act as a nucleophile, share its electrons here, push these electrons onto the oxygen, giving us this species. Water can now act as a base, grab off one of these protons, put these electrons back here, and we have this neutral tetrahedral intermediate. Well, we still have some H3O+ floating around, so if one of these oxygens grabs off a proton, then we're just going backwards. And that's going to happen. These are all equilibrium arrows. But if this oxygen grabs the proton, then we get something different. And that brings us to this species. Next, these electrons can collapse back in to reform the carbonyl, pushing away methanol as the leaving group, giving us this protonated acid and the alcohol. And finally, water can act as a base, grab off this proton, put these electrons back onto the oxygen, and we get our carboxylic acid plus our alcohol, and we have H3O+ again, right? So we started out with H3O+, but we regenerated our H3O+, so all that's needed is a catalytic amount of acid. Ester hydrolysis can also be carried out under basic conditions, and this is called saponification. Because long-chain fatty acids could be treated with sodium hydroxide, for example, to form soaps. So the term saponification is derived from the words for soap making. So ester hydrolysis under basic conditions is called saponification. And this is a reaction that you will be investigating in lab very soon. What's going on? So if this follows nucleophilic acyl substitution, then we're going to start out where hydroxide is going to share its electrons with the carbonyl carbon, pushing these electrons up onto the oxygen, giving us this. Sorry, I should fill in more details. Giving us this intermediate. Next, these electrons can fold back in, and if the hydroxide is kicked out, then we're just coming back here. That's going to happen. But if the methoxide is kicked out, then we get something new, which is this plus methoxide. Finally, methoxide can grab off a proton, so we have an acid-base reaction. Oops, sorry, I forgot the chlorine here. We have an acid-base reaction, which gives us this plus methanol. Actually, each of these steps is an equilibrium step, and it's this last step, because of the different pKa values between a carboxylic acid and an alcohol, this equilibrium lies very far toward the products, so this pulls the entire equilibrium for the reaction toward the products. Now I said this is the mechanism if it goes through nucleophilic acyl substitution. But number one, you shouldn't trust that it goes through nucleophilic acyl substitution. And number two, what I should have said is that this is a possible mechanism because we can never prove a mechanism. But let's go back to the first issue that you shouldn't just trust me. So let's think about some evidence. So here we have a few experiments where we can try to determine whether the reaction proceeds by maybe an SN2 type or nucleophilic acyl substitution. So if we started out with our ester radiolabeled at this position, and this is treated with hydroxide. If this was an SN2 type of reaction, then this would add here, pushing away this as a leaving group, and so we would expect to find the label in the carboxylate. But if it is nucleophilic acyl substitution, then hydroxide adds here, this goes up, this comes back down, this is kicked out, so that means that the radiolabel would end up on the alcohol. And what was observed experimentally is this. Therefore, it's consistent with nucleophilic acyl substitution, and it disproves SN2 reaction. Now here's another example, and in this case we have a chirality center in the alcohol part of our ester. So if this was an SN2 type of reaction, then hydroxide would add here, kicking this out as a leaving group. But because this is SN2, we would get inversion of configuration. So we would expect this product as our alcohol. But if it is nucleophilic acyl substitution, these electrons go up, they come back down, they kick out here, and no bond is broken to the chirality center, right? This bond is broken, not this one, so we would expect retention of configuration. And experimentally, this was found. Now here's a third example where the reaction was carried out, in this case acid catalyzed, and radiolabeled water was used. So if this was an SN2 reaction, then this would add here, these electrons move here, and so we would expect the label to be here. But if it's nucleophilic acyl substitution, then we get this. And so we would expect our radiolabel to be here. What's observed experimentally is we get this. So why does it end up in both places? Let's think about the mechanism. So the oxygen is going to grab a proton, and then water is going to add, we'll have a couple proton transfers, but this is going to give us an intermediate that looks like this. Where this is the labeled oxygen. And actually, let's go one step ahead to where this is protonated. So what happens next? One possibility is that these electrons fold in, push away methanol as a leaving group, and that gives us, skipping a couple steps, but that will give us this acid. And another possibility is that these electrons are the ones that fold in, kick this out as a leaving group, and after some proton transfer steps, we end up with this. So it's important to think about the details of the mechanism. What does this really mean if this is labeled? And what does it mean for the dissociation of the tetrahedral intermediate? Normally, it doesn't matter whether it's the one that we've drawn on top or the one that we've drawn on the bottom. But keep in mind that both of them will react. And if there is a difference between them, then that difference will be observed in the final product. Finally, we are on our last category of carboxylic acid derivatives, the amides. So these are the least reactive, so they cannot be converted into anything else. They can only undergo hydrolysis to form a carboxylic acid. So let's consider the mechanism of amide hydrolysis under acidic conditions. So our carbonyl oxygen can grab a proton, and so we have our protonated amide, which makes the carbonyl carbon more electrophilic, so water can add to the carbon, push these electrons up onto the oxygen, giving us this protonated intermediate. Another molecule of water can grab off a proton, putting the electrons back onto the oxygen, giving us this tetrahedral intermediate. Either oxygen can grab a proton, and we're just going backwards, but when the nitrogen grabs a proton, we get to this intermediate, and now either one of these oxygens, the red one or the blue one, these electrons can fold back in, kick out the amine, giving us this protonated acid and the amine. But this is going to be followed up with an acid-base reaction where the amine is going to grab off a proton, put these electrons back here, giving us our carboxylic acid and a protonated amine. So this is amide hydrolysis under acidic conditions. Finally, let's take a look at amide hydrolysis under basic conditions. So under basic conditions, we're going to have both hydroxide and water. Hydroxide is a much better nucleophile, so this is going to add to the carbonyl carbon, pushing these electrons up onto the oxygen, giving us this intermediate, and then these can grab off a proton, putting these electrons on here, giving us this tetrahedral intermediate. Under basic conditions, you are not going to have an O+, but it is possible to have an N+ because of the different pKa values. So the nitrogen can grab off a proton so that we have this protonated species, and now hydroxide could grab off a proton, allowing these electrons to fold in here to reform the double bond, pushing away the amine as a leaving group, giving us the amine plus our carboxylic acid. Keep in mind we have hydroxide around. Hydroxide will act as a base, grab off this proton, put these electrons onto the oxygen, giving us the carboxylate plus water, and this equilibrium lies very much toward the products. So this takes care of our look at nucleophilic acyl substitution reactions to convert acid chlorides into anhydrides or esters or amides or acids, to convert anhydrides into esters or amides or acids, etc. Being able to predict the products is important. You want to make sure you are moving from less stable toward more stable carbonyl. I want you to understand the mechanistic details sufficiently to be able to predict or explain some mechanistic details. So for example, on slide 28, when we were looking at evidence for the mechanism of ester hydrolysis, I want you to be able to predict the location of the radiolabel. I want you to be able to explain the position of the radiolabel. I want you to be able to predict and explain whether you have retention or inversion of configuration. And so knowing the big picture of formation of tetrahedral intermediate and dissociation of tetrahedral intermediate, that is very important to have those big mechanistic ideas. Being able to work through the more granular details is also important, not because I want to trip you up on a particular proton transfer step, but to be able to understand experimental evidence.